dead star no wider than a city, spinning 160 times a second. Beams of radiation sweep from its poles. A lighthouse made from the wreckage of a sun. In 1992, 2 astronomers in Puerto Rico found something impossible hiding in its signal. Planets. Not 1, 2. Orbiting a star that had already exploded. The first worlds ever confirmed beyond our solar system. Circling a corpse. For years, much of the scientific world refused to believe it. Then one prediction offered the universe a chance to answer for itself. What came back would reshape our understanding of where worlds can exist, and what the dead can still create. Tonight, we trace the search, decode the signal, and step inside a graveyard that became a birthplace. If you enjoy this, consider subscribing. It makes a real difference. The dead star is waiting. Let us begin. For as long as human beings have looked upwards, they have wondered whether other worlds exist. The question is older than telescopes, older than mathematics, older even than the scientific method itself. More than 2,000 years ago, the Greek philosopher Epicurus wrote that the universe must contain an infinite number of worlds, some like ours, some unlike anything we could imagine. Giordano Bruno, centuries later, argued that every star in the sky might be a sun with its own planets. He was burned at the stake in 1600 for his trouble, though not for that idea alone. The conviction that our world could not be the only one has threaded through human thought for millennia. But conviction is not evidence. And for most of that history, the question remained exactly where it started, unanswered and unanswerable. By the 20th century, the tools had finally begun to catch up with the ambition. Astronomers no longer had to wonder in the abstract. They could measure. They could track the positions of stars with extraordinary precision, looking for the faintest gravitational tug of an unseen companion. A wobble so small it would betray the presence of something massive and dark in orbit. The idea was elegant. The execution was punishing. No one embodied this pursuit more completely than Peter van der Kamp. A Dutch-born astronomer who spent his career at Swarthmore College in Pennsylvania, Van der Kamp dedicated decades to studying a single dim red star just 6 light-years from Earth, Barnard's star. Using the refractor telescope at Sproul Observatory, he painstakingly accumulated thousands of photographic plates spanning nearly 50 years, searching for microscopic shifts in the star's position that might reveal an orbiting planet. In 1963, he announced that he had found one, a Jupiter mass world completing one orbit every 24 years. It made headlines. The New York Times ran the story the following day. For a brief and thrilling moment, it seemed as though the oldest question in astronomy had been answered. It had not. The evidence began to crack within a decade. In 1973, John Hershey, working at the same observatory, discovered that every star in the photographic field appeared to wobble in exactly the same way. The signal Van der Kamp had attributed to a planet was coming from the telescope itself, a systematic error introduced by adjustments to the lens. Rolf Heinz, Van der Kamp's own successor at Swarthmore, published a series of increasingly damning analyses from 1976 onwards, demonstrating that the data could not support the existence of any planetary companion. The supposed wobble was an artifact of optics, not gravity. Van der Kamp never accepted it. He published refined claims as late as 1982, insisting that his planets were real. He returned to the Netherlands and died in 1995, still convinced he had been right. He was not the only one to fall short. Other astronomers had reported planetary signals around 61 Cygni, Lalande, 21185, and several more nearby stars. One by one, each claim was scrutinised, challenged, and discarded. By the end of the 1980s, there was not a single confirmed planet beyond our solar system. Not one. 5 decades of searching had produced nothing but false starts and cautionary tales. The field did not just lack a discovery, it had developed a scar. Any future claim would face a level of scrutiny born not from curiosity, but from the memory of being wrong. The answer, when it finally came, would arrive from the last place anyone expected, not from a living star with warmth and light, but from something that should have been incapable of harbouring worlds at all. To understand how, we need to understand what happens when a star dies. Not all stars fade gently. A star with more than roughly 8 times the mass of our Sun lives fast, burns through its nuclear fuel in a few million years, and ends in violence. When the fuel runs out, the core collapses under its own gravity in less than a second. The outer layers are blown outward in a supernova, an explosion so luminous it can briefly outshine an entire galaxy. What remains at the centre is something profoundly strange. The core, crushed beyond the point where atoms can hold their shape, becomes a ball of neutrons packed so tightly that a volume the size of a sugar cube would weigh roughly 1 billion tons on Earth. This is a neutron star. It carries roughly 1.5 times the mass of the Sun, compressed into a sphere no wider than a mid-sized city, about 10 kilometres from edge to edge. The numbers are difficult to hold in the mind, and that is because they describe something genuinely alien to everyday experience. A neutron star is not simply dense. It exists at the boundary of what matter can be before it ceases to be matter at all. But density alone is not what makes a neutron star remarkable. What makes it useful, what makes it one of the most extraordinary instruments in the universe, is what happens when it spins. When the original star collapses, it conserves its angular momentum. The same principle that makes an ice skater spin faster when they pull their arms inwards operates here, but at a scale that defies intuition. A star that once rotated lazily over the course of days is compressed into an object 10 kilometers across, and its rotation accelerates to dizzying speeds. Some neutron stars spin once every few seconds. Others, the millisecond pulsars, spin hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. These rapidly spinning neutron stars carry magnetic fields of staggering intensity, trillions of times stronger than Earth's. Charged particles trapped in these fields are accelerated along the magnetic poles and flung outward as focused beams of electromagnetic radiation. As the star rotates, these beams sweep across space like the beams of a lighthouse. If one of those beams happens to cross our line of sight, we detect it as a pulse, a brief, regular flash of radio energy arriving with mechanical precision. This is a pulsar, a dead star broadcasting its own heartbeat into the void. The regularity of that heartbeat is the key to everything that follows. Pulsars are among the most accurate natural clocks in the known universe. Millisecond pulsars, in particular, maintain their timing with a stability that rivals and in some cases exceeds the best atomic clocks on Earth. Every rotation produces a pulse. Every pulse arrives on schedule. And if something disturbs that schedule, if the pulsar is not alone, if something nearby is pulling on it, shifting its position by even a tiny amount, the disturbance shows up in the timing. Not as a gap, not as a silence, but as the faintest delay or advance in the arrival of a pulse. A discrepancy measured in millionths of a second, accumulated over months and years. Jocelyn Bell Burnell first detected the pulsing signal of a neutron star in 1967, working as a graduate student at Cambridge. The regularity of the signal was so unexpected that her team initially labelled the source LGM1, Little Green Men, half in jest, half in genuine bewilderment. It was Arecibo Observatory in Puerto Rico that confirmed the following year that the pulsar at the heart of the Crab Nebula was flashing every 33 milliseconds, far too fast for a white dwarf. The lighthouse model, a spinning neutron star sweeping its beams, became the accepted explanation. And with it came the realization that these objects were not just exotic remnants of dead stars. They were precision instruments. Nature had built a clock, and it was ticking at the heart of every pulsar in the sky. What no one yet imagined was that the ticking itself might carry a secret, that hidden inside the rhythm of a dead star's rotation, something impossible was waiting to be found. The Arecibo Observatory sat in the hills of northwestern Puerto Rico, cradled inside a natural limestone sinkhole surrounded by dense tropical forest. Its dish, 305 metres across, roughly the area of 20 football pitches, was the largest single aperture radio telescope on Earth from the day it opened in 1963, until China completed its 500-metre aperture spherical telescope more than 50 years later. The dish itself could not move. It was fixed into the ground, a vast concave surface of perforated aluminium panels reflecting radio waves upward toward a 900-ton receiver platform suspended 150 metres above, on cables strung between 3 concrete towers. To observe different parts of the sky, the receiver could be repositioned along a curved track, but the dish stayed where it was, a giant ear permanently tilted toward the heavens. For decades, Arecibo was the most sensitive radio telescope in the world. It mapped the surface of Venus through its clouds. It discovered ice in the shadowed craters of Mercury. It tracked asteroids tumbling past Earth. And it listened, with extraordinary precision, to the rhythmic signals of pulsars. For Alexander Wolszczan, a Polish astronomer who had arrived at Arecibo in 1983, the observatory was the ideal place to do the work he cared about most, hunting for new pulsars and studying the ones already known. In early 1990, that work was interrupted. A routine structural inspection of the telescope revealed cracks in the steel cables supporting the suspended receiver platform. The memory of a recent disaster hung over the decision that followed. In 1988, the 300-foot radio telescope at Green Bank in West Virginia had collapsed without warning, a catastrophic failure that shocked the astronomical community. Arecibo couldn't risk the same fate. Routine observations were suspended. The telescope was shut down for repairs that would last several weeks. The dish could no longer track objects across the sky, but it could still listen. If the receiver was parked at a fixed position, the rotation of the Earth would slowly sweep different parts of the sky through the telescope's field of view, turning Arecibo into a transit instrument, passively recording whatever drifted overhead. It was not ideal for targeted observations, but for a wide area survey, it was remarkably efficient. Wolszczan saw an opportunity. He had long wanted to search for millisecond pulsars at high galactic latitudes, away from the dense plane of the Milky Way, where most pulsar surveys concentrated their efforts. The theory predicted that old, recycled neutron stars should be distributed more or less evenly across the sky, not confined to the galactic disk. But testing that prediction required a significant amount of telescope time, and under normal operating conditions, Wolszczan would have struggled to secure enough. With the telescope effectively idle, and most outside observers unable to use it, his proposal was accepted. He was granted roughly a third of Arecibo's available time for close to a month. The survey worked. Wolszczan found 2 new pulsars relatively quickly. One of them, a millisecond pulsar spinning once every 6.2 milliseconds, located roughly 2,300 light-years away in the constellation Virgo, carried the catalogue designation Pulsar B 1257 plus 12. It was, by every initial measure, a routine discovery. Another fast-spinning neutron star to add to the growing catalogue. The real work, the careful, patient work of timing its pulses and characterising its behaviour, would come next. And that is where the story changed. Millisecond pulsars are almost always found in binary systems. The standard picture is straightforward. A neutron star in orbit with a companion, usually a white dwarf, gradually accretes material from that companion over millions of years. The infalling matter transfers angular momentum to the neutron star, spinning it up to rotational speeds of hundreds of revolutions per second. The result is a millisecond pulsar, old, fast, and extraordinarily stable. Because these pulsars typically retain their binary companions, their timing data shows a clean, predictable signature. The pulsar moves in its orbit around the pair's shared centre of mass, and the pulses arrive earlier or later in a smooth, periodic pattern that matches the orbital dynamics of 2 bodies. Pulsar B 1257 plus 12 did not behave this way. It appeared to be alone. No visible companion, no obvious binary partner. That was unusual but not unheard of. What was genuinely strange was what Wolszczan found when he began the detailed timing analysis. He measured the arrival times of 4,040 individual pulses, building a precise model of the pulsar's behaviour over weeks and months. The model should have been clean. Millisecond pulsars, left undisturbed, keep time with a regularity that borders on the eerie. Every pulse should arrive exactly when predicted, with deviations so small they are measured in microseconds. The pulses from Pulsar B 1257 plus 12 were not arriving on time. The deviations were tiny, fractions of a millisecond, but they were consistent. They were periodic, and they did not match any known binary configuration. Wolszczan examined the residuals, the difference between when each pulse was predicted to arrive and when it actually did, and found not one periodic signal buried in the data, but 2. One with a period of approximately 66.5 days, another with a period of approximately 98.2 days. 2 distinct rhythms layered on top of each other, imprinted into the timing of a dead star's rotation. He worked through the alternatives systematically. Could the variations be caused by seismic activity within the neutron star itself? A quake rippling through its crystalline crust and momentarily altering its spin? The pattern did not fit. Neutron star quakes produce abrupt, one-off glitches in timing, not smooth periodic oscillations sustained over months. Could the pulsar be part of an eclipsing binary system, with a companion periodically blocking or distorting the signal? There was no evidence of eclipses, no dimming, no companion detectable at any wavelength. Could the pulsar's spin axis be precessing, wobbling like a top, and producing an apparent timing variation? The mathematics did not support it. Could something in the pulsar's magnetosphere, the churning envelope of plasma and magnetic field surrounding it, be producing periodic interference? Nothing in the known physics of magnetospheres could generate 2 independent periodicities with the stability observed. One by one, the alternatives fell away. What remained was the explanation that no one was looking for, and very few were prepared to believe. The timing variations were caused by the gravitational influence of two unseen bodies in orbit around the pulsar. Each body tugged the neutron star toward itself as it orbited, shifting the pulsar's position by a tiny amount, toward Earth on one side of the orbit, away from Earth on the other. That motion compressed the pulses slightly when the pulsar moved toward us, and stretched them slightly when it moved away. Two bodies, two orbits, two periods. The signal was not noise. It was not an error. It was the gravitational fingerprint of two planets. Wolszczan ran the numbers. The inner body had a mass of at least 2.8 times that of Earth, orbiting at a distance of 0.36 astronomical units with a period of 66.5 days. The outer body was slightly heavier, at least 3.4 Earth masses, orbiting at 0.47 astronomical units with a period of 98.2 days. Both orbits were nearly circular. Both planets sat closer to their pulsar than Mercury sits to our Sun, and both were, by any reasonable definition, impossible. They orbited a star that had already exploded, a star whose death should have annihilated everything around it. Wolszczan understood what he was looking at. He also understood what the scientific community had just been through, and what it would take to make anyone believe him. 6 months before Wolszczan began preparing his results, another astronomer had stood before the world and made the same kind of claim. In July of 1991, Andrew Lyne, a distinguished British physicist and director of the Jodrell Bank Observatory at the University of Manchester, published a paper in Nature alongside his colleague Matthew Bales. The paper announced the detection of a planetary companion orbiting the pulsar B 1829-10, a slowly rotating neutron star roughly 30,000 light-years away in the constellation Scutum. The proposed planet was substantial, approximately 10 Earth masses, moving in a nearly circular orbit with a period of almost exactly 6 months. If confirmed, it would be the first planet ever detected beyond our solar system, the first proof that worlds existed around other stars. The reaction was immediate and electric. Theoretical papers followed within weeks, proposing mechanisms by which such a planet could have formed or survived the supernova that created its host star. The discovery felt like the beginning of a new era. It lasted less than a year. As the months passed, Lyne and Bales continued to refine their analysis, and somewhere in that process, a quiet, devastating realization took hold. The timing model they had used to extract the planetary signal required precise correction for the motion of the Earth around the Sun. Every pulsar timing measurement is affected by our own planet's orbit. As Earth moves toward a pulsar, pulses arrive slightly compressed. As it moves away, they arrive slightly stretched. This effect must be subtracted with exacting precision before any residual signal can be attributed to a companion body. Lyne's team had made the correction, but they had treated Earth's orbit as a perfect circle. It is not. Earth's orbit is slightly elliptical, and the difference, small though it is, introduces a subtle periodic signal with a period of 1 year and a harmonic at 6 months. The planet they had detected, with its 6-month orbital period, was not orbiting the pulsar at all. It was the ghost of Earth's own motion through space, improperly removed from the data. The error was not careless. It was the kind of mistake that hides in the deepest layers of a complex analysis, invisible until you know exactly where to look. But its consequences were absolute. The planet did not exist January 1992. the American Astronomical Society meeting in Atlanta. Andrew Lyne walked to the podium and did something that the scientific community would remember for decades. He retracted his discovery, publicly, clearly, without equivocation. He explained the error, described how it had been found, and stated plainly that there was no planet around pulsar B 1829-10. The hall, packed with astronomers who had followed the story with fascination for months, responded not with scorn, but with something far more remarkable. They rose and applauded. Some accounts describe it as a standing ovation. The response was not for the discovery was gone. It was for the courage it took to stand before your peers and say that you were wrong. In a field still bruised by Peter van der Kamp's decades of refusal to acknowledge his own errors, Lyne's honesty landed with the force of a cleansing act. But it left behind a shadow. The astronomical community had now been burned twice in a generation. Van der Kamp's phantom planet around Barnard's star, Lyne's phantom planet around a pulsar. The appetite for bold claims about new worlds had curdled into something closer to dread. The next person to announce an exoplanet would not merely need good data. They would need data so clean, so robust, so thoroughly tested against every conceivable alternative that the community would have no room left to doubt. That person was already in the room. Alexander Wolszczan had been scheduled to present at the same meeting. The timing was extraordinary, almost cruel in its dramatic precision. On the same programme where Lyne dismantled his own discovery, Wolszczan stood up and presented evidence for two planets orbiting a different pulsar entirely. The atmosphere in the hall had shifted within hours. The audience that had just applauded one astronomer for admitting his planets were not real was now being asked to believe that another astronomer's planets were. The paper followed swiftly. Wolszczan and Dale Frail published in Nature, volume 355, pages 145 to 147, under the title A Planetary System Around the Millisecond Pulsar PSR1257 plus 12. The findings were precise and specific. Two planet-sized bodies, with minimum masses of 2.8 and 3.4 Earth masses, orbital distances of 0.36 and 0.47 astronomical units, periods of 66.5 and 98.2 days, nearly circular orbits. The data came from months of painstaking timing observations with the Arecibo radio telescope, the same instrument that had found the pulsar in the first place. Wolszczan's case was built differently from Lyne's, and the differences mattered enormously. Pulsar B 1257 plus 12 was a millisecond pulsar, spinning once every 6.2 milliseconds, rotating more than 160 times per second. That extraordinary rotational speed made its timing data far more precise than anything achievable with the slower pulsar Lyne had studied. The timing residuals were cleaner, the noise floor lower, and the planetary signals correspondingly sharper. More critically, Wolszczan's data contained two independent periodicities, 66.5 days and 98.2 days, neither of which matched the 6-month or 1-year periods that would indicate contamination from Earth's orbital motion. The very error that had destroyed Lyne's claim could not plausibly produce the signals Wolszczan had found. The Polish astronomer Bohdan Paczynski, one of the most respected astrophysicists of his generation, reportedly called the discovery the greatest achievement by a Polish astronomer since Copernicus. It was a grand statement, and Paczynski was not one to make them lightly, but grand statements were easier to make than to accept. For much of the community, the reaction was not celebration. It was wariness, a deep institutional hesitation born from everything that had come before. The planets Wolfschan described orbited a neutron star, the collapsed remnant of a supernova explosion. That explosion would have been catastrophic beyond human comprehension. For a brief period, the dying star would have radiated more energy than every other star in its galaxy combined. The shockwave would have torn through the surrounding space at thousands of kilometers per second, obliterating anything in its path. The idea that planets could exist in the aftermath of such destruction struck many astronomers as physically implausible. Not merely surprising, implausible. These were not planets orbiting a warm, stable, life-giving star like our Sun. These were worlds circling a tiny, spinning, intensely magnetized corpse. A stellar remnant no wider than a city, radiating beams of high-energy particles from its poles. Whatever these objects were, they did not fit any existing model of where planets should be found. And so the question that followed Wolfschan out of that Atlanta conference hall was not whether his data was interesting. Everyone agreed it was interesting. The question was whether anyone should believe it. The resistance to Wolfschan's discovery was not irrational. It came from three directions at once, each reinforcing the others, and together they formed a wall of skepticism that would take years to dismantle. The first was technical. The retraction of Lyne's pulsar planet was not a distant memory. It had happened at the same meeting, on the same day, in the same room. The mechanism of that failure was still fresh in every astronomer's mind. A subtle error in modelling Earth's orbit had conjured a planet from nothing. Wolfschan's two-planet model was built on different foundations and did not share the specific flaw that had undone Lyne's work. But the broader lesson was harder to shake. Pulsar timing is a game of extraordinary precision, and precision creates fragility. The signals attributed to planets were tiny, variations of microseconds embedded in a stream of data that had to be corrected for the pulsar's own spin down, for its motion through the galaxy, for the rotation and orbital motion of the Earth, for the drift of electrons in the interstellar medium between here and there. At every stage, an error in any one of these corrections could, in principle, mimic or mask a planetary signal. The community had just watched one such error destroy what was supposed to be the discovery of the century. The idea that another, subtler error might be hiding in Wolfschan's data was not paranoia. It was experience. The second source of doubt was conceptual, and it ran deeper. For decades, the search for exoplanets had been guided by a simple and powerful assumption. Planets form around young, stable, hydrogen-burning stars, in the same way they formed around our Sun. You start with a cloud of gas and dust. It collapses under gravity. A star ignites at the centre. The leftover material settles into a rotating disk, and from that disk, over millions of years, planets coalesce. This is the story of our own solar system, and there was every reason to believe it was the universal story. The first exoplanet was supposed to confirm that narrative, a Jupiter or an Earth orbiting a sun-like star, proof that our cosmic neighbourhood was not unique. Instead, Wolfschan was offering something that fit no part of that picture. His planet orbited a dead star. Not a star in the process of dying, not a star that might one day die, but a neutron star. Something that had already exploded, already shed its outer layers into space, already collapsed into an object so extreme that the physics governing its surface belongs to nuclear theory rather than classical astronomy. How could a protoplanetary disk survive a supernova? How could planets form where there was no disk, no warmth, no gentle accumulation of dust over aeons? The answer, for many astronomers, was that they could not. The signal had to be something else. The third source of resistance was less scientific and more human, though no less powerful for it. There was a feeling, never quite stated openly, but present in the texture of the conversation, that the first exoplanet should mean something. It should tell us that other solar systems exist, that other Earths might be out there, that the architecture of our own planetary family is a common design replicated across the galaxy. Planets around a pulsar told none of those stories. They were curiosities. Exotic objects in an exotic environment, as far removed from the question of whether life might exist elsewhere as it was possible to be. Even if the data held up, even if the planets were real, they felt like the wrong answer to the right question. Some astronomers openly expressed the view that pulsar planets, whatever they were, should not be counted as true exoplanets, that the term should be reserved for worlds orbiting main sequence stars, stars that were still alive, stars that had something in common with the Sun. This was not a fringe position. It was widespread enough that when Michel Mayor and Didier Queloz discovered a planet around the Sun-like star 51 Pegasi 3 years later, many treated it as the true first, the discovery that really opened the door. The 2019 Nobel Prize in Physics was awarded to Mayor and Queloz for their work. Wolszczan and Freyl were not included. The committee acknowledged the pulsar planets, but the prize went to the detection around a living star. The distinction was never formally explained, but its implications were felt clearly enough. None of this made Wolszczan's data less real. The two periodicities in the timing residuals were clean, distinct, and stable over months of observation. The known sources of systematic error had been tested and excluded. The signals did not correlate with any artifact of Earth's motion, any instrumental effect, or any known astrophysical phenomenon other than orbiting bodies. The data did not care whether the community was ready for it, but science, rightly, demands more than data. It demands reproducibility. It demands prediction. It demands a test that the universe itself can pass or fail, independent of the hopes or doubts of the people asking the question. Wolszczan knew this, and buried in his own data was the seed of exactly such a test. A feature of the two planets' orbits that, if they were real, would produce a measurable and unmistakable consequence. One that no artifact, no error, and no coincidence could fake. To understand the test and why it was so decisive, it helps to first understand what the pulsar timing method is actually measuring, and why it is, in a quiet and unassuming way, the most sensitive planet detection technique ever devised. Imagine a lighthouse on a distant shore. Its beam rotates with perfect regularity, and every time it sweeps past your position, you see a flash. If you time those flashes precisely enough, you can build a model of the lighthouse's rhythm, predicting exactly when the next flash will arrive, down to the fraction of a second. Now imagine that the lighthouse is not fixed on its foundation. Imagine that something heavy and unseen is pulling on it, dragging it slowly toward you, then slowly away, then toward you again, in a repeating cycle. When the lighthouse moves toward you, the flashes arrive slightly earlier than predicted. When it moves away, they arrive slightly later. You never see the thing doing the pulling, but you know it is there, because the timing tells you so. A pulsar is that lighthouse. Its beams sweep the sky with every rotation, and each time one of those beams crosses Earth's line of sight, a pulse of radio energy is recorded. For a millisecond, pulsar like pulsar B, 1257, plus 12, this happens more than 160 times every second. Over days, weeks, and months, the accumulated timing data builds into an extraordinarily detailed record of the pulsar's behaviour. A record precise enough to detect a shift in the pulsar's position of just a few hundred metres across a distance of 2,300 light-years. If a planet orbits the pulsar, it does not simply circle the neutron star while the star sits still. Both the planet and the pulsar orbit their shared centre of mass, the gravitational balancing point of the system. For a planet with a few times the mass of Earth orbiting a neutron star with 1.4 solar masses, that centre of mass sits very close to the neutron star itself, and the pulsar's resulting motion is tiny. But tiny with this method is enough. The pulsar moves toward Earth by a small amount on one side of the planet's orbit and away from Earth by the same amount on the other side, and that motion compresses and stretches the arrival times of its pulses by a few microseconds. Spread across the planet's full orbital period, those microseconds trace a smooth, sinusoidal curve in the timing residuals. The difference between when each pulse was predicted to arrive and when it actually did. This is what makes pulsar timing so remarkably powerful. The measurement does not depend on seeing the planet. It does not depend on the planet blocking any light, or reflecting any light, or emitting any light. It depends only on time, on the ability to measure when a pulse arrives, and to notice when that arrival deviates from the model. The precision is breathtaking. A millisecond pulsar's timing can reveal the presence of a companion body with a mass smaller than that of Earth's moon. In principle, it could detect an asteroid. No other planet-finding method comes close to that sensitivity at the low mass end. The radial velocity technique, which would later be used to discover planets around Sun-like stars, works on a similar principle. The star wobbles under the gravitational pull of its planet, and that wobble shifts the wavelengths of the star's light. But starlight is noisy. Stellar atmospheres churn and pulsate. Spectral lines blur and shift for reasons that have nothing to do with orbiting companions. The radial velocity method, for all its power, struggles to detect planets much smaller than Neptune around quiet stars, and it fails entirely around active or rapidly rotating ones. Pulsar timing has none of these limitations. The signal is clean, the clock is natural, and the sensitivity is, in the right circumstances, almost absurdly high. The limitation is not sensitivity, it is opportunity. Pulsars are rare. Millisecond pulsars are rarer still. And planets around pulsars, as the following decades would demonstrate, are rarer than almost anyone anticipated. The method can see what no other method can, but only if there is something there to see. In the case of pulsar B1257 plus 12, there was. And the two somethings that Wolfsjan had found carried within their orbits a gift that no instrument could have manufactured and no error could have simulated. The orbital periods of the two planets, 66.5 days and 98.2 days, sit in an almost exact 3:2 ratio. For every 3 orbits completed by the inner planet, the outer planet completes almost precisely 2. This is not a coincidence. It is a resonance, a gravitational relationship in which 2 orbiting bodies periodically align and exert a stronger than usual pull on each other. Orbital resonances are well understood in our own solar system. Pluto and Neptune are locked in a 2-to-3 resonance. 3 of Jupiter's largest moons, Io, Europa, and Ganymede, maintain a 4-to-2-to-1 chain. The physics is the same wherever gravity operates, and it carries a testable consequence. Within months of Wolfsjan and Freyle's announcement, a team of 4 physicists, Frederick Razio, Philip Nicholson, Stuart Shapiro, and Saul Tucholsky, published a paper in Nature laying out exactly what that consequence should look like. If the two planets were real, their near 3-to-2 resonance would cause them to gravitationally perturb each other in a specific and predictable way. Each time the inner planet lapped the outer one, the gravitational interaction between them would nudge their orbits slightly, altering their eccentricities, tugging their orbital periods a fraction of a second longer or shorter. These perturbations were small, but they were not random. They followed a precise mathematical pattern dictated by the masses, distances, and orbital mechanics of two real bodies influencing each other through gravity. The pattern would build over time, growing more detectable with each passing month. The beauty of this test was its specificity. An artifact of delta processing cannot gravitationally perturb itself. An error in the timing model cannot evolve in a way that precisely mimics the interaction of two massive bodies locked in a resonance. No instrumental glitch, no mismodelled correction for Earth's orbit, no magnetospheric fluctuation can reproduce the exact signature of Newtonian gravity operating between two planets over years of observation. If Wohlstein could detect those perturbations, and if they matched the predictions, the debate would be over. Not resolved by consensus, not settled by reputation, resolved by the universe answering a direct question with an unambiguous answer. Wohlstein returned to Arecibo and began a systematic campaign of timing observations that would stretch over 3 years. Pulse by pulse, month by month, the data accumulated. The timing residuals from pulsar B, 1257, plus 12 were tracked with painstaking care, and gradually a new signal began to emerge from within them. Subtle, exactly where it was predicted to be, growing in amplitude at exactly the rate the physics demanded. In 1994, Wohlstein published his results in Science. The title was measured and deliberate. Confirmation of Earth mass planets orbiting the millisecond pulsar PSRB 1257 plus 12. The word confirmation was chosen with care. This was not a new claim. It was the fulfillment of a prediction. The gravitational perturbations between the two planets had been detected. Their magnitude and timing matched the theoretical models to a degree that left no plausible alternative explanation. The 3-to-2 resonance was real. The planets were real. The same paper announced a third discovery. Buried deeper in the timing data, at a shorter orbital period of 25.3 days, was the signature of something even smaller. A body with a mass of roughly 2/100ths of an Earth mass, somewhat less than twice the mass of our Moon. It was the least massive planet detected by any method at the time, a world so small that calling it a planet stretched the conventional meaning of the word. It would later be named Drauga, an undead creature from Norse mythology, a fitting label for a ghost of a world orbiting a ghost of a star. 3 planets, confirmed not by a single observation, not by repeating the same measurement and hoping the answer held, but by the internal gravitational logic of the system itself. The universe had been asked a question: are these planets real? And it had answered in the language of orbital mechanics, in a dialect that could not be faked. The first planetary system ever confirmed beyond our Sun was not a family of gas giants orbiting a warm yellow star. It was 3 small, radiation-scorched worlds circling a spinning stellar corpse in the constellation Virgo, discovered by a Polish astronomer who had been given telescope time because the instrument was broken. The debate over whether the planets existed was settled. The question of how they could possibly be there was only just beginning. The planets were real, but reality only deepened the mystery. 3 worlds orbiting a neutron star, a stellar corpse that had been born in one of the most violent events the universe can produce. The supernova that created pulsar B1257+12 would have released more energy in a few seconds than the Sun will emit across its entire 10 billion year lifespan. The blast wave would have torn through everything in its vicinity: gas, dust, rock, ice, accelerating it to thousands of kilometers per second and scattering it into the surrounding interstellar medium. Any planets that had orbited the original star before the explosion would not merely have been damaged, they would have been annihilated, vaporized, returned to atoms, and dispersed across light years of empty space. So the 3 planets circling the pulsar could not be survivors. They had not weathered the storm. They had not clung to their orbits while the star exploded around them. The physics simply does not allow it, which meant they had to be something else entirely, something that came after. Worlds that had not existed before the supernova. Worlds that had been born from whatever was left behind. The leading explanation, and the one that has held up best over 3 decades of scrutiny, is a process called second-generation planet formation. The idea begins not with the supernova itself, but with what the neutron star was doing before it became a millisecond pulsar. Millisecond pulsars do not spin at 160 rotations per second on their own. A newly formed neutron star typically rotates much more slowly, perhaps a few times per second. To reach the extraordinary spin rates of a millisecond pulsar, something must have accelerated it. That something is almost always a companion star. In a binary system, if one star collapses into a neutron star while the other is still evolving, there comes a point where the companion swells and begins shedding its outer layers. That material falls toward the neutron star, spiraling inward in a disk and transferring angular momentum as it goes. Over millions of years, this steady rain of stolen matter spins the neutron star up, faster and faster, until it reaches the millisecond range. The process is called recycling, and it is the standard explanation for how millisecond pulsars come to exist. But pulsar B1257 plus 12 is alone. It has no companion. If it was once in a binary system, and it almost certainly was, something happened to its partner. The most widely accepted scenario is that the companion was a low-mass white dwarf, and that the interaction between the 2 stars eventually became catastrophic. Perhaps the neutron star's gravity disrupted the white dwarf entirely, tearing it apart and spreading its material into a disk of debris around the pulsar. Perhaps the 2 objects spiraled inward and merged. Either way, the outcome is the same. The companion was destroyed, and its remains formed a ring of material encircling the neutron star. From that ring, planets formed. Not in the way planets typically form around young, hydrogen-burning stars, where a vast cloud of primordial gas and dust slowly collapses over millions of years. This was a different kind of birth, a second genesis from recycled material. The debris disk around the pulsar would have been composed of heavier elements, the processed remnants of a star that had already lived and died. Carbon, oxygen, silicon, iron. From this wreckage, through the same basic physics of accretion and gravitational collapse that builds worlds everywhere else, new planets condensed. Small, rocky, radiation-blasted worlds that had never known warmth from a living star. The theory is elegant, and it is supported by at least one compelling piece of independent evidence. In 2006, a team using NASA's Spitzer Space Telescope detected an infrared excess around the magnetar 4 U0142 plus 61, a young, highly magnetized neutron star roughly 13,000 light-years away. That infrared signal was consistent with a disk of dusty material orbiting the object, precisely the kind of debris structure from which second-generation planets could, in principle, form. It was not a direct observation of planet formation around a neutron star, but it demonstrated that the raw material for such a process can exist in exactly the environment where the theory predicts it. Other pulsar planet systems, rare as they are, hint at different formation pathways entirely. Pulsar J 17 19 14 38 b, discovered in 2011, appears to be the crystallized remnant of a white dwarf that was not so much destroyed as stripped. The pulsar's intense radiation and tidal forces peeled away the companion's outer layers over millions of years, leaving behind a dense, carbon-rich core, an object sometimes described, with only modest exaggeration, as a planet-sized diamond. It was not built from a disk. It is the skeleton of a dead star, reclassified by circumstance. Then there is Pulsar B 1620-26b, known informally as Methuselah, a gas giant roughly 2.5 times the mass of Jupiter, orbiting a neutron star and white dwarf binary in the ancient globular cluster Messier 4. With an estimated age of roughly 12.7 billion years, it is one of the oldest known planets in the galaxy. It almost certainly was not formed in its current location. The prevailing view is that it was captured, gravitationally acquired during a close encounter in the dense, stellar environment of the cluster. A wanderer that found a home among the dead? Each of these systems tells a different story, and together they paint a picture that would have been unthinkable before 1992. Planet formation is not a delicate, contingent process that only happens under perfect conditions around well-behaved, sun-like stars. It is robust, opportunistic. It happens in the aftermath of supernovae, in the wreckage of stellar mergers, in the ancient hearts of globular clusters, and in environments so hostile that the word habitable does not even begin to apply. The universe, it turns out, is extraordinarily good at making worlds, even when it has to build them from the ruins of something else. That insight was one of the first gifts of Wolfsjan and Freyle's discovery. But for all its scientific importance, the detection of planets around a dead star did not ignite the revolution that the field had been waiting for. That revolution would come 3 years later from an entirely different direction, using an entirely different method, and it would arrive with its own impossible surprise. In October of 1995, Michel Mayor and Didier Queloz stood before an audience at a conference in Florence and announced that they had found a planet orbiting a star called 51 Pegasi. The star was 48 light-years away in the constellation Pegasus. It was not a neutron star, not a white dwarf, not any kind of exotic remnant. It was a quiet, middle-aged, hydrogen-burning star. A star so similar to the Sun in mass, temperature, and luminosity that it could almost have been its twin. This was the detection that the community had been dreaming about for decades. A planet around a normal star. A solar system that might look something like ours. Except it looked nothing like ours. Mayor and Queloz had used the Elidé spectrograph, mounted on the 1.93 metre telescope at the Observatoire de Haute-Provence in southern France, to measure tiny Doppler shifts in the star's light. The shifts revealed a wobble, a rhythmic back and forth motion caused by the gravitational pull of an orbiting companion. The wobble was large, roughly 70 meters per second, and the period was astonishingly short, 4.2 days. The planet completing one full orbit of its star in just over 4 Earth days. The numbers pointed to something that should not have existed, a gas giant with roughly half the mass of Jupiter, orbiting just 7 million kilometres from the surface of its star. For context, Mercury, the closest planet to our Sun, orbits at 58 million kilometres. This planet was more than 8 times closer. Its surface temperature would have exceeded 1,000 degrees. It was a world of scorched hydrogen, a gas giant baked in the glare of its parent star. Nothing in the existing models of planetary formation allowed for this. The prevailing theory, built on decades of studying our own solar system, held that gas giants could only form far from their star, beyond the frost line, where temperatures were cold enough for volatile ices to condense and begin the process of runaway accretion that builds a gas giant's enormous mass. A Jupiter-sized planet in a 4-day orbit was not just unexpected, it was a contradiction. And yet, the data was clean, the signal was strong, and within a single week, Paul Butler and Geoffrey Marcy at Lick Observatory had independently confirmed it. The discovery of 51 Pegasi b, the first of what would come to be called hot Jupiters, did not just add a new planet to the catalogue. It demolished the assumption that our solar system was a template for how planetary systems should look. The universe had produced something no one had predicted, orbiting exactly the kind of star everyone had been watching. What followed was an avalanche. Butler and Marcy quickly announced additional planets around other Sun-like stars. Within 2 years, the number of confirmed exoplanets reached double digits. The techniques improved, the surveys expanded, and the field that had spent decades finding nothing was suddenly finding worlds everywhere it looked. Exoplanet science, almost overnight, became one of the most productive and exciting frontiers in all of astronomy. In that rush of discovery, the pulsar planets were quietly set to one side. They were acknowledged, respected, occasionally cited, but they were not the foundation on which the new field was built. The revolution was driven by radial velocity detections around Sun-like stars, and later by the transit method and space telescopes. When the 2019 Nobel Prize in Physics was awarded for the discovery of exoplanets, it went to Mayer and Queloz. Wolszczan and Frail were not included. The committee did not dispute that the pulsar planets were first, but the prize was given for the discovery that transformed a field, for finding the planet that opened the floodgates. There is something uncomfortable in that distinction, and something worth sitting with. Otto Struve, the Russian-American astronomer who spent his career at the Yerkes Observatory and later at the University of California, had proposed as early as 1952 that Jupiter-sized planets in close orbits might exist and could be detected by their gravitational effect on their host stars' spectral lines. The idea was largely ignored for over 4 decades. When Mayer and Queloz found exactly the kind of planet Struve had imagined, it was treated as a revelation, a bolt from a clear sky. In fact, it was a vindication of an idea that had been waiting patiently for the instruments to catch up. The same could be said of Wolszczan's discovery. The pulsar planets were not curiosities. They were proof, the first definitive proof, that the universe builds worlds beyond our own. That distinction belongs to them, regardless of what came after. The revolution may have been triggered by 51 Pegasi b, but the door was opened 3 years earlier by a Polish astronomer reading the timing residuals of a spinning corpse of a star in the constellation Virgo. In the 3 decades since Wolszczan's confirmation paper, the number of known worlds beyond our solar system has gone from 3 to more than 6,100. The acceleration is almost impossible to overstate. What was once the loneliest question in science, are there other planets out there, has become one of the most abundantly answered. NASA's Kepler Space Telescope, launched in 2009, stared at a single patch of sky for years, watching for the faint periodic dimming of starlight that occurs when a planet crosses in front of its host star. It found thousands. Rocky worlds smaller than Earth. Gas giants in tight orbits. Planets circling binary stars. Planets in the habitable zone where liquid water could theoretically persist on the surface. Kepler did not just discover individual worlds. It revealed, statistically, that planets are more common than stars in our galaxy. The Milky Way alone contains hundreds of billions of them. The TESS mission, launched in 2018, expanded the search to nearly the entire sky, surveying the brightest and nearest stars for transiting planets. The James Webb Space Telescope, the most powerful observatory ever placed in space, has begun doing something that would have seemed like fantasy in 1992, analysing the atmospheres of distant worlds, detecting the chemical fingerprints of water vapour, carbon dioxide, and methane in the skies of planets orbiting other stars. The question is no longer whether other worlds exist. The question now is what those worlds are made of, what their skies look like, and whether any of them harbour the conditions for life. The diversity of what has been found defies every expectation the field once held. There are lava worlds where the dayside surface is a molten ocean of rock. There are super-Earths, planets larger than our own but smaller than Neptune, a category that does not even exist in our solar system. There are mini-Neptunes shrouded in thick hydrogen atmospheres, water worlds with oceans potentially hundreds of kilometres deep, and planets so close to their stars that their atmospheres are being stripped away in real time, trailing behind them like the tails of comets. The universe did not build copies of our solar system. It built everything imaginable, and then several things that were not. And yet, in all of that abundance, worlds like the ones Wolfsjan found remain extraordinarily rare. Despite the pulsar timing method's unmatched sensitivity at the low mass end, its ability to detect objects far smaller than anything a transit survey or radial velocity measurement could find, only a handful of additional pulsar planets have ever been confirmed. The vast majority of pulsars, it turns out, have nothing orbiting them at all. The conditions that created the system around pulsar B1257, plus 12, the disruption of a companion, the formation of a debris disk, the slow coalescence of new worlds from recycled stellar material, appear to be genuinely uncommon. Wolfsjan himself spent decades searching for another system like it. He never found one. The discovery that opened the age of exoplanets remains, to this day, almost singular. In 2015, the International Astronomical Union gave the system its formal names, chosen through a public naming campaign. The pulsar itself became Lich, an undead creature from mythology, a being that commands the dead. Its planets became Draugr, Poltergeist, and Forbitor, an entire family named for ghosts and revenants, orbiting a star that died long ago. It is difficult to imagine a more fitting tribute. These are not living worlds. They are not places where oceans gather, or atmospheres breathe, or sunlight falls on green hills. They are small, radiation-scoured, airless bodies circling a city-sized remnant of a star that tore itself apart. They exist in a place where nothing should. On the 1st of December, 2020, the Arecibo telescope collapsed. The cables that had held the 900-ton instrument platform above the dish for nearly 6 decades finally gave way, and the structure fell, punching through the reflector below, and destroying one of the most important scientific instruments ever built. The telescope that had found the first planets beyond our solar system no longer exists. Its dish lies in pieces in a Puerto Rican sinkhole, slowly being reclaimed by the forest. but the three worlds it found are still there. Poltergeist, Phobator, and Draugr continue their quiet orbits around Lich, 2,300 light-years from Earth, in the constellation Virgo. The pulsar still spins, 160 times every second, its beams still sweeping the sky, its clock still ticking with a precision that shames the finest instruments humanity has ever built. The planets still tug on it, gently, predictably, their gravitational signatures still written into the arrival times of every pulse. They were the first, not the first planets anyone expected to find, not the first planets anyone wanted to find, and not the planets that launched 1,000 missions or won a Nobel Prize. But they were the first confirmed worlds beyond our sun, and they were found not by looking where the light was brightest, but by listening, carefully, patiently, over months and years, to the rhythm of a dead star, and noticing that something, against all expectation, was alive in the silence around it.